Good morning. I want to thank all the distinguished professors here and the deans and the vice rector for very kind words. Today I'd like to introduce to most of you who have not heard about Memristors. We'll talk about the past, the present, and the future. But let me begin with the present, and the present I would consider to be April 30, 2008, when HP, which all of you know, had a press conference. And this press conference was conducted by Dr. Stanley Williams, who is shown here. He was the director of the Information and Quantum Laboratory at HP. And it is quite unusual, I believe, that HP has a press conference on a new invention of theirs. And so this particular press conference was to show to the world that HP has built the world's first Memristor. And this was a slide that I had borrowed from Dr. Williams. And in that press conference, he has shown an example of the HP product. This is an example of an array. Think of a grid, and this is just one of them, and it's a Memristor. And you can see the size of that one Memristor is approximately 17 nanometer. And just to understand how small is 170 nanometer, Dr. Williams showed a picture of the actual size of the world's smallest known virus. And this is the diameter of 25 nanometer. So already in 2008, SB has produced a Memristor that is smaller than the world's smallest virus. So you can imagine how many such Memristor can be squeezed into a tiny chip. And the press conference was conducted on April 30 to announce that there will be a paper published the next day in Nature, which is May 1st. May 1st. And it will be about the Memristor. So for those of you who did not know what Memristor means, this is just a name to mean memory resistor. So it's just an abbreviation or a contraction of memory resistor. So everything you see today has to do with memory or some kind of memory. In this press conference, Dr. Williams announced that the paper that would appear the next day, May 1, is going to be called, the title of the paper, by the way, but these are the authors. Stan Williams is the director responsible for this new project from HP. And the title is The Missing Memristor Found. And it is called Memristor Found because it was referring to a paper that I have published 37 years earlier, 1971. And the title of the paper is Memristor, the Missing Circuit Element. In 1971, I had postulated that such an element must exist and it is essential. But no one has been able to build a solid-state Memristor at that time. In fact, it took 37 years for HP to build this device, and it was completely forgotten for 37 years until this new invention was announced. I was told by Dr. Williams that 1 month later, of course this news was in the newspaper all over the world after the press conference, and I was told that 1 month later, June 1, remember the Nature paper is May 1. 1 month later, I was told by Dr. Williams that Google had already registered more than 1 million inquiries on the Memristor. And according to Dr. Williams, this is the most heavily blogged science story of the decade. So the question I guess you might want to know is why such immense interest, especially on something that is quite technologically oriented, why so much interest within 1 month? And the reason for that, the answer is that the Memristor, as you will see today, is a non-volatile memory. It means you do not need batteries to store memory. And non-volatile memory are estimated to be a $250 billion industry next year. And so there are many reasons why this is so important. But one of them, imagine a PC that will turn on instantly in the morning. Right now, if you have a PC and you want to turn on in the morning, you put on the power and you will have to wait maybe 5 minutes for the computer, the PC to start working. With Memristor, in a few years from now, you will turn on instantly. And another reason is, let's say you are writing, and you have spent half an hour writing a love letter to your girlfriend. And suddenly your girlfriend calls and come over right away. You just spent half an hour, so right now you have to install it before you leave, and so that's a tremendous waste of time. With the Memristor, you will just turn off the switch. You visit your girlfriend, and maybe you come back next month or next year. You turn it on, your love letter will still be there, will continue. This is why Memristor is such an important device. And one of the things that it will replace, all of you, of course, are using sticks right now. Stick is a non-volatile memory, and it will eventually replace, the Memristor will replace not only the sticks, but it will eventually replace DRAM, and it will even replace hard drives. So there will be a technological revolution, in my opinion, in a few years' time. So, but most immediate is that the stick is going to be replaced very soon. Why? This is called a flash memory. Why not continue to use this? Well, first of all, there are many disadvantages that you may not realize. Flash cannot be scaled down below 20 nanometer, for example, and it has very poor retention time in the sense that it will fail. After about 10,000 or even 100,000 times, it will fail. It's also very slow, and it is power hungry. This is why your cell phone have to be kept charging every 2 days or so. It is power hungry. If you would replace it with Memristor, you could use your cell phone or iPad for many more hours. But one thing that you must realize is that flash memories, these sticks that you have been using, is a short-term memory, in the sense that memory is not permanent. They will lose about 20% information after every 10 years. And so, therefore, this is just for a temporary memory. You will never want to store your family pictures on such device because it will disappear. It will not be permanent. On the contrary, HP has estimated that their invention of the Memristor, which is based on titanium dioxide, has a retention time that would be more than 100 million years, which is practically infinity. And so, in a sense, we can say that like diamonds, you always say diamonds are forever. You can say titanium dioxide membranes are forever because it is permanent, at least in principle. Now, in the same Nature paper, there was another short article. Usually, Nature is journal. Whenever they found an interesting article on invasion that they believe would be fundamental, they would ask another group of experts to write an evaluation and a criticism. And this was by Tour and He, and it's called the fourth element. That's the title of that two-page article on the same issue, May 1, 2008. So why is it called the fourth element? And of course that was because all of you have learned, I assume most of you are engineers here, you know there are three classic elements: capacitor, from the date of the discovery, 1745, it's the first electrical element invented, called capacitor. Then Ohm in 1827 invented the resistor. Then Faraday invented inductor. And now Memristor is 71. So he is referring to this fourth element. Why is the Memristor considered the fourth element? How can it be mixed up with the three elements already known? So the question is, you have to understand first, what is a resistor? What is a capacitor? And what is an inductor? These are the three classic elements. Most of you probably believe that you knew what they are. And for example, in all textbooks you have learned that resistor is just something obeying Ohm's law with that symbol. And V is R is called a resistance. And capacitor with that symbol is some circuit element that obeys the equation I is capacitance C, V dt. And the inductor with that symbol is an element that obeys voltage is L, the inductance, di dt. So you may think that you know everything certainly about the resistor, inductor, and capacitor. But unfortunately, if you extend the application to something more general, for example, the capacitor, if you take this classical definition, current I is C dV dt, and if you replace this capacitor by something that is time varying, as you realize capacitor is a plate. If you move that plate as a function of time, so C becomes a function of time, and you will ask to find what is the current when you apply a voltage. So the natural thing to do is, because you have only learned capacitor is IC dV dt, and you put simply the same equation, and you put psi a function of time, you of course get a waveform. But the problem is the waveform is going to be wrong, in the sense that if you measure this in the laboratory, you will find the waveform is totally different from that. So there is something wrong, in other words, with the definition when the device is time varying or when it is nonlinear. And so when I realized this in the late 60s, I realized that there was no definition, no correct definition of even the three most classic elements. So I decided that I had to first produce a definition that would be correct, in the sense that when it is linear time invariant, you would get the same answer. And when it is time varying or nonlinear, you would still get the same answer. This is what I call axiomatic definition. For those of you who may not know what axiomatic definition is, it is something that is with a minimum requirement. For example, this is a definition that let's say you are a historian, or if you are an expert in English literature, social science, you don't know anything about science, you will still know what the circuit element is by axiomatic definition. So this is how it's defined. Imagine you have a device, consider even a piece of rock from Mars. You happen to get this rock and you believe that maybe it can conduct electricity. So you attach two wires. And now you say, what is this device? What can it do? What application it has? The axiomatic definition is to take this device, right now I call it a black box because you don't know what's inside, and you would connect this with anything, any electrical circuit, maybe a battery or any circuit, and you would want to measure or observe in an oscilloscope what is the voltage and the current. But for an axiomatic definition, you are supposed to know nothing. And so you don't even know what, you're not supposed to even know what voltage or current is. You're not even supposed to know what electrons is. So in axiomatic definition, we simply start by assuming in axiomatic approach, you start with names. And you say that this name means that, and then everything must follow from that assumption. So for all of you here, the two names that you need to know is an ammeter and a voltmeter. You don't have to know what it is. It is something you can buy in an electronic store. You can go and say, I want to buy a voltmeter and I want to buy an ammeter. That's the action. That's all you have to know. And it simply means that if you connect any terminal to a voltmeter, you will read some voltage, and you can put this also in the oscilloscope, and you can see the waveform. And that waveform is called the voltage signal. So voltage now is defined axiomatically as something you read from a voltmeter without knowing anything else. So if you are a sociologist, a historian, you just buy a voltmeter, and anything you mention is voltage. You don't have to know anything about electrical engineering. Same thing. If you connect an ammeter in series with a wire, anything you measure is called ampere, the current. So you now have current and voltage, the axiomatic definition. And now you put in any signal. You have, imagine, any possible signal, voltage source, current source, or any circuit, and then you can measure a waveform in the oscilloscope called the current waveform and the voltage waveform. This together is called an admissible signal pair. So in other words, you make one experiment, you have a signal pair. And then you change the voltage waveform, you change the circuit, you get another one. And you imagine, so this is a Gedanken experiment. Something you don't actually can do in a lab, but you can imagine that you perform this experiment and you have a collection of all of these waveforms. That is what this device is. It's completely described this device. It's a collection of all admissible waveforms. Why is this complete? Because imagine that you can store all of this information. Then if I give you this device and I give you the circuit and I say what is the voltage and current, you can predict this because the correct answer will be one of the memory that has been stored. So you just look up table, you look at, if this is current, this must be input. So this is why this is completely defined by admissible signal pair. But because this is not practical, the practical situation is that there are some devices where the admissible signal pairs does not have to be stored because it happens to obey some relationship. And such a relationship can occur in 4 possible situations. So imagine now, first of all, because you can measure the voltage and the current, which is now well defined because we know it's from voltmeter and ammeter, that's axiom. You can integrate, of course, the voltage with a computer, and the integral of that, we use the symbol flux and phi, and we give it a name flux. Or you can give it another name. You don't have to know anything about physics, about flux. It's just a name. And you can integrate also the current, and we use the symbol Q, and we call it charge. You don't have to know anything about charge. It's just a name given to the integral of that. So now you have 4 basic variables from the axiomatic approach, and you now consider, suppose an example, I call this an admissible voltage current signal, AVIS, like the AVIS rent a car, so you can easily remember. Admissible. So imagine you have a collection of all possible admissible signal of a device, and you found out that for that particular device, luckily, they all obey a relationship. So it always follows a straight line. And if that's the case, then we call that a resistor, and that's just Ohm's law. V is equal to Ri, R is the slope of the straight line. But it could also be following a nonlinear curve, such as this curve in the voltage current plane, or such as that curve. As long as all the admissible signal pairs obey a relationship, that device is called a resistor. So you now know the system is, and in that case, we will have this symbol, and we will say that device is a resistor, and this is a collection of all voltage and current that obey that relationship. And I call that an A-path, admissible, VI, Avis path is A-path. So that's what the conceptual meaning of a resistor. Now, maybe another device did not have a relationship between voltage and current, but it has a relationship between the voltage and the charge. So in that case, we would call this a linear capacitor. The equation would be the linear, in the linear case, it would be just like the classical definition. But it could also be a nonlinear curve. As long as the admissible signal pair obeys a relationship in the voltage and charge plane, it is called a capacitor. Similarly, another device may happen to have a relationship that obeys a relationship between flux and current. And the slope, let's say, is L, and that happens to be V is L di dt in the linear case. Or if it happens to be nonlinear, as long as it is a relationship between the flux and current, it is called a nonlinear inductor. So I now have the picture of three basic circuit elements. If I now so this is a diagram to remember because it's very simple. It's just a symbol, a symbolic diagram, no concept involved. If you just put voltage, current, and integral current is the charge, the integral voltage is flux. You have four quantities that you already know what it is by axiomatic definition. And if you have a device that is related only by voltage and current, we call that a resistor. That's the first element. If it is related by voltage and charge, it is a capacitor. If it is an element that relates only between the flux and the current, it is the inductor. So we have now defined the three classical elements, and in a linear case, it will be exactly what you just learned. In the nonlinear case or ternary case, it will give you the correct answer. So this is the correct definition. But if you use this axiomatic approach, you will see that by logic, there is a missing relationship. There must be another element that has not been found. So that missing link, is the memristor. So therefore now, a memristor is now formally defined as a device where the admissible signal pairs obeys a relation between the flux and charge plane, and in any relationship as long as it's between flux and charge. And that's the symbol that I introduced in 1971. So we now complete the diagram. This is therefore why it's called the fourth element in Nature article. And this is the axiomatic reason for that. Now, it turns out that this axiomatic approach is not new. I did not invent an axiomatic approach. The inventor of that, at least, goes back to Aristotle, 350 BC. Aristotle was, of course, a very clever person, as all of you know. And he was asked by his students, what is nature? But matter, what does matter come from? Today we talk about what electrical elements come from. How do you define them? In Aristotle's time, nothing is new about electrical elements, but his student asked, what are the matter come from? And so Aristotle simply said that simple, there are only 4 items to define: air, water, fire, and earth. Just like we have 4 quantity: water, current, charge, and fire. He said there are 4 basic quantities. This is the axiom. And so these are the axioms. But then Aristotle said you can define the different properties of this by 2 of the 4 possibilities. In other words, this given the matter, you can ask, is it moist? Is it very moist, like watery? Is it dry? How dry? Is it very cold? Or it is hot? So he said these are the attributes. So these are the 4 relationships that we have. These are the 4 circuit elements. For example, if you this analog, so this is the voltage, current, flux, charge. And Aristotle said, how do you know you have water or earth or fire? From there he said very simple. Each of these will have 2 properties only. 2 of the 4 properties. So Aristotle says, if the material is both dry and hot, it is fire. If it is between moist and hot, it is air. If it is moist and cold, it is water. If it is dry and cold, it's earth. So if you now draw a diagram of what Aristotle says, this is the diagram. Aristotle's 4 building blocks of nature is fire, it's related between dryness and hotness. So these are 4 attributes: dry, cold, moist, and hot. And if it's both cold and dry, it's earth. And if it is both hot and moist, it's air. And Aristotle even realized that this is so fundamental, you must have a symbol to denote that. So the symbol he picked are the Platonic symbols. So for example, a square, hexagon, tetrahedron would be the symbol for that. And so are the other octahedron would be the symbol for air, and icosahedron would be the symbol for water. So you can see now the analogy of the 4 building blocks of matter and my 4 building blocks of electrical engineering. It is just a change of name and symbol. So I have to say Aristotle invented this axiomatic approach and we just followed him. Now, so you can now use this axiomatic approach and make a symbolic diagram. If you symbolically think of this alpha, it's an integer, 0, 1, 2, minus 1, minus 2, and beta, 0, 1, 2, and minus 1, minus 2. And this is just the symbol. So for example, a resistor, which will be located at 0 and 0, here, I would have the symbol 0, 0. It means that the voltage, you do not integrate or you do not differentiate the voltage, it's just 0. So both, if you relate both 0, 0, or voltage and current, is a resistor. If it relates between 0 minus 1, which is, you can see that it is minus 1 integral of the current. Remember, beta is current. You integrate the current is charge, and 0 is voltage. That is a capacitor. Similarly, inductor is minus 1 and 0. And now memristor is here. It's between minus 1 and minus 1. If you use the axiomatic definition, it's obvious that there are even more elements. So for example, if you take minus 1, minus 2 and minus 1, you can show that this element is what I call the memory inductor. If you pick this element below here, and it is minus 1, minus 2, it is called a memory capacitor. So not only we have memristor, we have mem capacitor, we have mem inductor, and even more. This is similar to a periodic table. And of course, all the other elements have not been found, but at least we now have 3 new elements, and they all have memory. Mem capacitor, mem inductor. And of course, this is exactly what Mendeleev did many years ago for chemical elements. And the same thing, this is the first table, periodic table, that Mendeleev published, of course, in Russian. in 1869. And in his table, Mendel had many gaps, like this one, that one, this one, and then more. But Mendel would say that if my theory is correct, then this element must exist. And of course, we now know that they all exist. This is the gallium, this is germanium, and this is scandium, and other elements, sodium, potassium, they all absent in the original table. They all have been filled. So, my periodic table is very similar to that. Okay, now let me go on to tell, now you know what the Memristor is, how it's defined, but what is a property? What is the difference of the property of Memristor from the resistor, capacitor, inductor? So we now look at carefully what is a Memristor does. So Memristor has to be relating between the flux and the charge. So let's call that phi is function of Q, F of Q. So for example, phi is equal to Q squared. That would be a square, or Q cubed. So every such nonlinearity defines a Memristor. Now, if you differentiate both sides of this equation, you have d phi dt is df dq, dq dt by chain rule. But we know dq dt is current by definition, I. We know d phi dt by definition voltage. So you can also say a Memristor is defined by voltage is M times I, which of course looks like Ohm's law. In fact, it is Ohm's law, except that with Ohm's law, this M is a constant. In a Memristor, it is a function of Q. And M of Q is just df dq, it's just a slope. So a Memristor is just defined by Ohm's law, with it, at each point, it is just the slope, the conductor. In this case, the resistance. And I call that memristor, memory resistance. Or if it's plotted in the Q phi plane, it will be memductance, or memory conductance. So this is, you can think of therefore Memristor is just a state-dependent Ohm's law. It means that the resistance is not constant, but depends on the state variable. The state variable happens to be Q in this case. It could be phi also. So remember, Memristor is the slope of the phi versus Q curve. So as an example, you can imagine a device, a Memristor that has only two straight lines, a piecewise linear, with slope 1, and this phi versus Q, the slope is in ohms. So within this range, this will be just 1 ohm, and beyond this range, it will be slope 10 or 10 ohms. So this particular Memristor with two segments of slope 1, 10 is equivalent to a new device that gives you only 1 ohm or 10 ohm depending on where you were before at time 0. So that's what the memory is. We now are going to use the resistance, the low resistance or high resistance as the memory. Right now, the reason when you turn off your iPad or your cell phone, all the memory disappears because the voltage becomes 0 and the current becomes 0. But in the case of Memristor, you can turn it off, but the resistance stays there. Either you are 1 ohm before you turn it off or 10 ohms. So this would be the future memory. Right now, all electronic devices from iPhone to iPad to computer is always using the voltage or the charge as the memory that disappears if you turn off the power. In the Memristor, if you choose the resistance or the conductance as the memory, then after you turn on the power, the memory remains there. That's why it's called non-volatile. You do not need the battery. That's the reason why it is so fundamental. That is why I believe this is why it will replace the future DRAM with the future even hard drive. Now, so why is it non-volatile? So I want to explain to you why. As you, for example, if this device happens to be a resistor, and you are turn on the power, apply a voltage, at time 0, you turn on voltage, you can say E, say 5 volt, and then delta second later, say 20 minutes later, you turn it off again. When the voltage becomes 0, the current becomes 0. This is a resistor. But if this is a memristor, even though the voltage turn off becomes 0 again, and the current 0, but in a memristor, it's not the voltage or current, it is the charge and flux. So you look for you integrate the voltage, and this is the flux. So even though the voltage is 0, the flux remains the same. So let us say that this happens to be at this value. So after you turn off the switch, this point stays there, and therefore the slope is, remember, the slope is in this case is the conductance. So the conductance is, remember, even though you have no battery. This is why it's non-volatile. Okay, now this is one property of a memristor as I define it. And I will now show you 3 different interesting properties that is very unusual and surprising for you. The first one is called a zero phase shift signature. So every memristor has a signature, just like when you sign something, you will have a unique signature. Every memristor has a unique signature. And you have a fingerprint that's unique. Every memristor has unique fingerprint. And I will tell you now what are the signatures. The first signature of a memristor is a zero phase shift. It simply means that, let's say the red waveform is the voltage, and the blue waveform is the current. If your input is a red voltage, and whenever the voltage goes to 0, the current will also go to 0 at the same time. So this is why there's no shift. In an inductor or capacitor, there is a phase shift. In the memristor, the voltage current must always go to the origin together at the same time. That's called the zero phase shift. It's a signature. Only memristor, I believe, that has this property. So, what about fingerprint? By the way, one of the consequences of that is, as you know, if you have a capacitor, the reason it has a phase shift is because if you have an initial capacitor and you suddenly connect that by a switch to a light bulb, the bulb is going to flash momentarily because it discharges the voltage. And this consequently you have a phase shift. In that the same thing, if you have an initial current and you switch suddenly to a bulb, it's going to light up momentarily. That's why this can store energy. But if you have a memristor, the zero phase shift property means that if you have initial charge or flux, you switch on the bulb, there's nothing. So it doesn't store energy. So that's the signature, zero phase shift. The second thing is it has a fingerprint. And the fingerprint is that, and this is almost a consequence of the zero phase shift. It means that if you apply any periodic signal, say a sine wave, voltage, and you measure the current, and you plot the relationship between the current and the voltage plane, you will always get a hysteresis loop, but the loop must always get to the origin. It's pinched, just like that pinch. I call it a pinch hysteresis loop. So pinch hysteresis loop is this unique fingerprint of a memristor. So these are the 2 important to remember. It has a zero phase shift signature, it has a pinch hysteresis loop. All memristors have this property. And another property of a memristor is that if you increase the frequency, as let's say at 1 kilohertz, you have a pinch loop like that. You can prove that if you use the same sine wave of the same periodic input, but you increase the frequency, say to 50 kilohertz, you will get another pinch loop, that of course have the same width here, but go through the origin, but the area becomes smaller. And at even higher frequency, say to 100 kilohertz, it will even be skinnier. And in fact, at extremely high frequency, the area becomes zero, becomes a straight line. So this is the fingerprints of a memristor. You know, it has pinch hysteresis loop, and not only that, the loop will shrink and shrink and shrink as you increase the frequency until it becomes a straight line. So this is another critical property of a memristor. I call them the fingerprints. Now, interesting, something also unusual. So all of these properties are very unusual. You want to know how does the memristor, all of this phase loop or the zero phase basically applying its waveform time function. What about DC? Well, normally you first, if you're an electrical engineer, first thing you want to do is you put a battery and then say what is the current, right? So if you do this experiment, you can ask what happened if you connect a battery to a memristor directly. What happened? Interestingly enough, or surprisingly enough, the thing you will see is smoke. That's what will happen. If you connect a memristor direct to the battery, if you have a memristor and you are willing to destroy it, you connect it. It's going to burn out immediately, almost instantly. And the reason why that is so is that if you apply a battery, it's just like a horizontal line, so the flux will be integrating. So the flux will keep going, it never stops, because you integrate it forever. This is a battery. And so let's say this is a charge versus flux curve of a particular memristor, and let's assume that the slope keeps increasing. The slope, remember, is the conductance. So that if this thing keeps going, this slope keeps increasing, so the resistance keeps decreasing, and eventually the ampere becomes too much, it's going to melt. That's the reason. So, and you can ask the same question if you apply. So if you apply a battery, you would have smoke, or if you apply a current source, you will also have smoke, some reason. So that you will never connect a DC current source or DC motor source direct to memristor, because you will just destroy it. So what is the DC VI curve of an ideal memristor? It's just one point. It's the point at the origin that is the DC VI curve, when it's unusual. You have a device, a DC, only one point is allowed without burning it. And that device actually turned out to be a well-known circuit element invented in 1961 by Professor Calabria. It has a name. It's called an annihilator. And it's not important for us to know what that is today, except that the memristor at DC is just consists of only one point. So at DC, a memristor is equivalent to a point, and this is just a symbol of an annihilator. And so that's also very unusual. Okay, now the question now is, can we, so far you now know all the property. It has zero phase shift, it has pinch hysteresis loop, the area shrinks, and it burns out at DC, so it has only one point. These are all unusual properties. Now the question is, how can we build such a device? In 1971, I have actually built that device as a proof of principle. Actually built one in my 1971 paper. Except that device I built using operation amplifiers and transistors, and in 1971, the operation amplifiers are quite big, so actually it's a big area just for making one memristor. This is what is totally useless. And the question is, can one build a solid-state memristor? Of course, SP finally built it in 2008. But it turns out that Josephson in 1973, received a Nobel Prize for something he invented when he was a sophomore. He was just like one of you here. He was a student at Cambridge University. He was very clever, and he understood quantum mechanics perfectly, and he predicted that a device must exist based on quantum mechanical principles, and that device will have a behavior that can be modeled by such a circuit here, and in particular, remember he was just a student like you. He was just a sophomore, and he published a 2-page letter in the Physical Review, and he proposed such a device would have this symbol. It would have a capacitor, an inductor, and a resistor. It would behave like this equivalent circuit. And then he said that it needs another component, and that component, he doesn't know what it is, but he said it relates between the current and the flux. Now, today you know that that is an inductor. He didn't know it, so he had a symbol like that. But it's not important that he didn't know that it was an inductor. Finally, this is the equivalent circuit, and after this 2-page paper was published, AT&T, or Bell Lab, engineers immediately built it because it's so simple, and it showed that exactly behaved almost exactly like predicted by Josephson junction. And he got a Nobel Prize soon after that. It was because it was proven that it is correct, and it was very useful device. And this is the shortest paper that gave rise to a Nobel Prize, 2 pages only. That should be an inspiration to some of you here. You know, you can be a Josephson, next Josephson. Now, after Josephson got the Nobel Prize, he decided to go back and make more careful study, and he found that he had actually neglected a term. He found out that there is a quantum mechanical quasi-particle pair interference current. So he published another paper as a correction to say that, to be more exact, you need another component, and that component has a current that is very small. In fact, it is almost always negligible, very small. This is why when Bell Lab built the device, they didn't feel anything different, but conceptually, in principle, Josephson say there is another current. And he doesn't know what that is, but he say it's something that relates the current and the voltage, just like Ohm's law, except that he said that, but the conductance is not constant. It depends on the flux. And now today we know that that is exactly the Memristor. So Josephson already in 1971, the same year that I published my paper, already had a Memristor, at least the model. And so one can say that Memristor already existed, but that's not conceptually, but it's not quite true, because it is not possible for anyone to go to a Josephson junction and pull out a device and this is my Memristor. It's just like, all of you know, protons are made of 3 quarks. 2 up quarks of charge plus 2/3, and 1 down quark, charge 1/3. That's a proton, but nobody can ever pull out a quark and say, this is my quark. They have to be always together, just by physical principles. They are too strongly connected. Okay? So therefore, it is not correct to say that Josephson gives you already Memristor. That it is only conceptually correct. So we have to wait 37 years for HP to finally build this device. This is the Nature paper. It is very simple. It's made of 2 type platinum electrodes, 2 wires coming out, and it is sandwiched by titanium dioxide. Titanium dioxide is a chemical that is white. Anything that's white is titanium dioxide. So this is an example. If you've never seen, if you're not a chemist, this is titanium dioxide. It is everywhere. on the white paint, there's like the white color. Anything that's white is made of titanium dioxide. That's why it's white. Okay, and I have to tell you a true story. A few years ago, when I always bring this to my demonstration, and at one time from San Francisco, I almost missed my flight because the security found it and thought I'm carrying cocaine. So what? This is a true story. So anyway, that is the titanium dioxide, and in the Nature paper, Dr. Williams and the SP group show that it obeys a relationship between flux and charge, which is a memristor. And so they built that. So this is the world's first memristor, and it is very small. As you remember, it's only 17 nanometer. And they show that it has the fingerprint, the signature, and the fingerprint. From HP paper in Nature, you can see go through 0, 0, 0, 10 times. That's the signature. And they also show that it has the pinch hysteresis loop, and it shrinks in area. So it has all the fingerprints of a memristor. It is therefore a memristor. The world's first memristor. Okay, now if you now consider this memristor that I show you as the future memory device, and that this stick, which is there are many companies, including Samsung and IBM, everybody is working on it, because the first company that can make this device inexpensively and reliably is going to be the leader. So anybody who uses this memory using resistance to build information is a memristor. And for that reason, this is why I showed you earlier, things like what they call DRAM, RRAM, phase change memory, they are all memristors because of that property. More recently, HP has published a picture like this. If you didn't know what that is, you may think this is a very tall building with many floors, but this is just a multi-layer chip that each layer is a memristor, array of memristor. And HP has demonstrated that it is possible in the future to build memristor not only in one layer but many layers in 3 dimensions. And it was estimated, for example, in a few years' time, the entire Library of Congress in USA, if you go to Washington, D.C., this is the world's biggest library. It contains 21 million books, or 10 terabytes. It has been estimated that it would take only maybe 10 layers to store every information in these books of the US Congress Library. That is truly quite amazing. And only a few this will be possible. Just last month, and this is already based on SP's 17 nanometer memristor. Just 2 months ago, a paper had been published. In fact, more than 2 months, in November, December, already it was 5 months ago. A group in USA published papers that shows a memristor that's only 8 nanometer, which is a very, very small size device. And in fact, just 2 years ago, a group, 2012, another press conference was called in Germany at the Karlsruhe Technical University, and they would announce that they can make the memristor with only 1 molecule. Also, you can now make even smaller, 1 molecule memristor. But of course, this is impractical right now. Unlike the 8 nanometer one, which is the real device, it will be almost extremely difficult to build this. But concept, they have been demonstrated in the laboratory. 1 molecule memristor can exist already. And so just last month, I was in Korea, and I was quite impressed to find a university in Korea, in particular Professor Choi from Jeju, and they have built a printable Memristor, which means that this is the picture. This is the real picture you are seeing here. This is the one. So we can bend this. So, and you can see they measure that it's a pinch stress loop. So they indeed can build Memristor by printing. So you can imagine that the Memristor is going to be very inexpensive to produce in the near future. Now, these are all ideal Memristor as I define it. But in 1971, but in 1976, Professor Kang, in his PhD thesis, Professor Kang is now the president, by the way, of the KAIST University in Korea. And in his PhD thesis, we have published a generalization of a device that behaves exactly like a Memristor. It has the signature of zero phase shift. It has phase hysteresis loop, but it is more general in the sense that they have more properties. And that device is called a generalized Memristor, and it's simple because it has all the properties, except now that, again, it's just an Ohm's law, except that in Ohm's law, this resistance is a function of only charge, one state variable. In this picture, we can generalize that to allow one or more state variable. It does not have to be charged. And then that state variable has to obey, of course, an equation. In the 1971 paper, this is charged. X is charged, so dq dt is just I. But everything is the same, but more general. And this is 1971. But the critical property that makes it a Memristor is that this equation has the zero phase shift property, and it's pinched. And if it's pinched, it's a Memristor. Now, once you realize this, after HP published the famous Nature paper, many researchers go back to the literature and went back more than 20 years and suddenly realized that there are many papers that have been published by papers, researchers who said, I have a non-volatile memory. But he didn't know, the researchers never know what it is, and they cannot plot the DCVI curve. Because you know why? Because it's burned, so there's no DCVI curve. But they always publish a pinch loop. And so a pinch hysteresis loop really is something that you should remember, something you can very quickly observe in the laboratory. And there are, in fact, many Memristors that were published already before HP, except that the author did not know it was a Memristor. And in fact, after I realized this, I went back much longer, and I now want to go back to 1800, before, say, 1790. London already was a very prosperous city then. The streets have now lighting in London in the 1700s, but the street lights are gas lamp. They are fire. This gas lamp. So toward the end of the 1700s, the English scientists began to ask maybe it's possible to build an electrical lighting, and it's been a big challenge. And the most successful person that I want to introduce you next is Sir Humphrey Davy, who happened to be a chemist. He was a very ingenious person. Among other things, he discovered sodium and he discovered potassium. Two elements was missing in Mendel's table. So he has many discoveries. But he also discovered or proposed that it should be possible to build electrical lighting. And his theory is to take two electrodes and he picked carbon, right? So he proposed if you take two carbon, right, and make it very near each other but not touching. And then if you apply a very big voltage, he estimated you need about more than 1,000 DC volt. Then there should be a spark. And with that spark, if you put it in the vacuum, you should have a lighting, electric bulb. This is the beginning by the light bulb. So he proposed that that is one way to build, to replace the gas lamp with electrical lighting, except that he doesn't have 1000 volt. And so now, come 1800, now we come to Italy, Alexander Volta. So Volta now has a role in the Memristor. Volta in 1800 discovered you can build batteries very simply, and he showed that you can just put them in series and you can have any voltage you want in 1800. So you can just get 1000 of that, and you get 1000 volt in 1800. This is such a great discovery that Napoleon invited. This is the true picture of Napoleon with Volta, Alexandra Volta, explaining to Napoleon how this works, how this battery works. Napoleon was, of course, a general, but he's also an intellectual. He loved science. He was very impressed. After demonstration, he made Alexander Volta a conte. He was a conte after that. And okay, so anyway, this is 1800. When Sir Humphrey Davis realized this, he built this device immediately in his laboratory in London. And of course, he didn't know what it is, except that it works. And I will show you, just last December, I was in Hong Kong, and I proposed an experiment with the famous laboratory in University of Hong Kong, and I suggested to repeat the experiment. So Professor Xu from from University of Hong Kong spent 2 months to order the parts. These are the 2 carbon rods, and then they can apply a voltage, and sure enough, when they applied that, they were able to produce a spark, and as I predicted to him, that if you measure, put it in a sine wave, you should measure the zero phase shift and the phase hysteresis loop. So you can see zero phase shift and the phase hysteresis loop. So this is the first proof that in 1801, 1 year after Volta invented battery, the device by Sir Humphrey Davis is already a Memristor. In fact, I now call the first man-made Memristor. Humphrey Davis knew about it. We have to wait for many more years later. Now I want to request a video to show you this experiment because it's of historic interest. It is the first man-made Memristor. Can I see this a video? This will be a very short video, just to show you the real experiment. And then you will see after the spark. The spark is so bright that the researcher has to wear a mask. Okay, you can see here the wear mask because it is so bright. Now you can see the spark. There should be sound as well. Listen carefully, there should be a spark, sound. You hear the sound. See how bright it is. And the next experiment will show you the pinch hysteresis loop. This was only last December. This experiment was made. Okay, now we will show you the measurement of the zero phase shift and the phase hysteresis loop. That's the phase hysteresis loop. Thank you very much. So the first man-made Memristor, in fact, existed in 1801. So which we ordered the elements. We have the capacitor in 1745. Memristor is earlier. Then the resistor, because Ohm had proposed his Ohm law only in 27. And then the Faraday is the last. The inductor was the last. Now, I will tell you now an interesting story that you would be interested to know. This is a true story. Then you see Sir Humphrey Davy, and there's Napoleon again. As I told you, Napoleon was a very fan of science. So he not only made Volta a Conte, he wanted to reward Sir Humphrey Davy for his discovery of many discovery, including this lighting, this charge. Okay, and but in 1808, France is at war with England. All the gunboats, the blockade. So how does Napoleon decided that he doesn't care about war? He deserves this medal. This is like the Nobel Prize. In his time, there were no Nobel Prize in 1800. So Napoleon said, this medal should go to this medal is the Pre-Napoleon Institute, should go to Sir Humphrey Davy. So he is a very thoughtful gentleman, not only general. He decided to issue a special visa for Humphrey to come to Paris to claim the prize, but he needed someone to bring this visa to Sir Humphrey. He had to go through the blockade, so he had to find someone that is knowledgeable how to get there. And then Humphrey would need a lot of money to travel, so he decided that if he bring a lot of French franc, it would be useless in England. Pound, here doesn't any pound, so he decided to bring gold coin. So he had a lot of gold coins, a sign of gold coin, for this gentleman to bring the visa with the gold coin, because gold is money everywhere. And then he suddenly realized that, but this is such an honor. Sir Humphrey Davy should bring his wife. He's a sir, so his wife, the lady, it's Lady Jane. So Lady Jane should come with Sir Humphrey Davy. So he added double the gold coin, so that to expenses. And so then it's such a thoughtful general, Napoleon said, but then wait a minute, we have to be comfortable. See, they need to have a servant. So he added more gold coins to hire a servant, for Sir Humphrey Davy to hire a servant to carry the luggages and help them all the way to Paris to claim the money. This is true story. I'm telling you this because you know who is the servant. The servant who carried the luggage is Faraday. It's a true story. Okay, you will never forget that. So this is interesting but true. Okay, now now I want to show you something different, because so far everything has been about memory, just remember things. But just to remember things is really not so exciting, because it's just like you put something, carve something on a stone, and it's permanent in a stone, like you go to the museum, it's permanent, but you cannot change it. But something interesting about Memristor is that it's much more than just memory. Here is an organism, animal, a snail in fact, and the snail is wearing a Nobel Prize medal. This is a true Nobel Prize medal. And I call this snail, by the way, escargot californica, because it's like escargot. And because the scientific name is more complicated, the scientific name is application scientifica. Okay, so we are now going to look at escargot californica. And why is this picture interesting? Why is there a Nobel Prize medal in there? Well, this is a true picture that Eric Kandel, when he went to accept the Nobel Prize in Stockholm, the first picture, when you get Nobel Prize, you're invited to give a lecture. In the lecture, Eric Kandel showed this picture. And he said that I dedicate this lecture to this snail because without him, he would not have been able to produce the molecular result of memory. It's all about memory. And this is a wonderful book. If you are interested about memory from a Nobel Prize winner, Eric Kandel is a beautiful book. And he talks about this snail and how he discovered the molecular basis of memory. And this famous experiment that Kandel reported is the following. The snail, the capricia, is a very delicate organism. It swims in the water, and it has a tube that comes out. This tube is normally external because it needs to breathe, the air. But it is such an instrument needed to the survival of the instrument. So whenever the appreciate detected some danger, it will immediately contract and hide inside the shell. And then, of course, a few minutes later, it will come out again because it has to breathe. This is called a cycle. So Eric Kandel was very clever. He picked this because it has very big neurons. In the 50s, it's hard. This is done in the 60s or so. It's hard to get things so small, but it has very big neurons. This is the reason why people appreciate. So he put in an electrode in the point. So you want to point this with a paintbrush. So this is a paintbrush. Just gently touch it, and you immediately contract. So obviously, there will be a sensor there. So he put in the sensor to detect the signal. So you've got to be an action potential to detect and then that signal would travel to the muscle. And so then he put another electrode on the muscle, so that the muscle, when it generates signal to contract the muscle, he would record that. So therefore, Kandel did 15 experiments. He put that, and then it's recorded immediately, the signal and the muscle, 2 signals. And then this thing would disappear, will hide. 5 minutes later, come out again, he would touch again. He did this 15 times, and he published 5 of the 15 measurements. So this is all taken from Kandel's famous Nobel Prize work. So these are the action potential. When you touch it, this is the action potential. There are 15 measurements. He published 5 of them. 1, 2, 5, 10, and 15, the last one. I have it in different color here, as you can see. And now, the interesting thing is following. Each of these signals are identical. This is an action potential. So they're always the same. It has no information. The information is in the part that triggers the muscle. And so you would expect that if you design an electrical instrument or electrical circuit, if you apply a signal, and you apply the same signal, you will get the same output all the time. You expect that. But Kandel found that in the measurement, in the first one he had a big signal, the muscle immediately contract. After 5 minutes later, when the thing comes out again, the same signal unchanged, but then he found out that the signal to contract muscle is not as big. And in fact, each one gets smaller and smaller until in the 15 days almost no signal. So he was quite an amazing scientist. He immediately realized that this is fundamental. This is learning. This is the first time we're talking about learning now, more than just memory. The Aplicia has learned that it is not so dangerous after all. So he doesn't have to worry so much. So the thing is getting smaller and smaller. And this is the classic experiment that led Kandel to the molecular basis of memory and learning. I used to give this talk in Paris, and there's a name, by the way, for this in English. It's called habituation. This is a technical name. And perhaps the simplest form of learning is habituation. All about what is habituation every day to help us learn not to attend or respond to irrelevant stimuli. I gave this talk many times in France and Paris, and of course the French doesn't pronounce habituation. Because habituation is very difficult for me to pronounce. So I give a nickname. I put it déjà vu response. It's the same meaning. Okay, déjà vu response. And now I have just shown you that we can do the same thing with a Memristor, and in fact with a very simple Memristor. Now I repeat the measurement. This is the bottom one, and they have simple potential. They are identical, but the top are the diminishing stimulus for the muscle, and it gets smaller and smaller. This is where the learning is. So if I now have a Memristor that has a Q versus phi curve that is monotonic, so the slope becomes smaller and smaller and smaller. And remember, this is charge versus flux. So the slope is conductance. So the conductance is smaller and smaller and smaller. Now if I apply 15 identical pulses, this is just like this signal here. Apply 15 of them, and the signal will be integrated to get this voltage. So you must get to the flux. So integrate this. So this is a ramp that keeps increasing monotonically. As it increases monotonically, you move up, so that the slope keeps changing, gets more and smaller. But the voltage is the same, 10 volt times the conductance. So the conductance gets smaller and smaller. The current will be smaller and smaller, and this is the corresponding current predicted by this simple circuit. And I just look at 1, 5, 1, 2, 5, 10, 15 with the same symbol. And you can see it has exactly the same behavior. I have just shown you a Memristor, the simplest Memristor can learn. And this learning is in fact nothing but the synapse. Those of you who know something about our brain know that our brain is made of synapses and axons. And the synapses is the memory, is the learning. When you learn how to walk when you were a baby, you are changing the synaptic waves, and which translates to you are moving along the charge curve, and you are changing the conductance as you learn. So, in fact, Memristor is essential for learning. It is the missing link needed to understand the molecular and cellular mechanism of memory. And this is a typical neuron. This is the neuron body. All these red dots are synapses. This is where we learn. These are now all Memristors. So I've just shown you the part of our brain that allows us to think and do intellectual things, become intelligent, are the neurons that you learn, and there's also the output that generates action potential. The output is this one. This is called an axon. The axon is the output, and I will show you in a few minutes' time that the axons are also made of Memristors. But before I do that, let me summarize that synapses are in fact nothing but Memristor from information perspective. Synapses are Memristor. And there are thousands, for every new, this is a true picture now. The other one was a drawing. This is the true picture of a neuron. Every of this dot is a synapse. For every neuron, there are more than 20,000 synapses. There's only one axon, okay? So if you want to build a machine that behaves like our brain, you will have to have many synapses, 20,000 more per neuron. And this is why it would have not been possible to build a brain-like machine now, because it is possible today to build these synapses, but the chip area needed for the present synapse is about the same area as the neuron, which is incredibly impractical. You have to be able to build synapses that are at least 1,000 times or 10,000 times smaller than the chip area before you can build the machine. I now show you that synapses are small enough that would have that property. So synapses is essential, and it is a correct building blocks to build a brain-like machine. Now, just to summarize, I just say that to build a neuromorphic computer approaching the synaptic density of the human brain, the electronic synapse must be smaller than 1/10 the size, or at least of the CMOS simulator. And the Memristor has that property. So now I want to summarize that what I've just shown you as significant, because as was already mentioned by one of our famous professors here earlier in the beginning, Feynman, all of you know Feynman, was famous. He's considered the father of nanotechnology. In 1960, he gave a famous talk, which everybody considered to be the beginning of nanotechnology. In 1960, things are very big. So Feynman essentially saying that there are much more things that one should look at, and that's why the title of his talk is that there is plenty of room at the bottom. The bottom means going to nano scale. In 1960, we're talking about micron, much bigger. So Feynman predicted that this should be possible someday. Now, of course, we can now make things that are much smaller. We can now make things in the at the bottom. We are now at the nano, which is 8 nanometer. Is almost at the bottom already. So this statement is Feynman, if he were alive, would be very disappointed. There is no more room, okay? But now, you can change the word room to smart. You can make it smart. You know, not only the Memristor is very small, but it can now create learning. And so this is one of the reasons why Memristor, in my opinion, is going to revolutionize the technology of the future. And Memristor, in other words, are much more versatile than the flash memory sticks. And so let me now move on to show you the next thing. I've told you the brain is made of synapses, and there are Memristor. Now I'm going to look at the axon. And the axon is the work of another Nobel Prize. This is the classic work for Haskell Huxley that got the Nobel Prize in 1965. They got the Nobel Prize by showing this is now, we're looking at a neuron, we're now looking at the axon. Now the axons is where the axial potential is generated. Haskell Huxley got the Nobel Prize by publishing in 1952 a fundamental paper that showed that it's possible to model this by like a transmission line with ordinary resistors with a circuit that people call the Haskell-Huxley cell. So every one of these two terminal, okay? This is the circuit, two terminal. So imagine now every one of these is a Haskell-Huxley circuit. And Haskell-Huxley proposed this circuit model and say that, and this is called the sodium ion channel this is called a potassium ion channel, because if you look under an electron microscope, you will see that the axon is actually made of many little openings, and those that will pass potassium is called potassium channel. Those that pass sodium is called sodium channel. And there's a distribution of that all over. In other words, the ion channels in fact are just water-filled biological sub-nanotubes formed by large protein molecules. So Haskin actually suggested in their model that the potassium and sodium ion channels can be modeled by this circuit, and they got a Nobel Prize because when they put this in a computer, they found that action potential was generated. No one before them, for more than 60 years, can produce a model or a circuit that will produce an action potential. Actually, as the first one to demonstrate that this model we're doing. And they have given the equation, by the way. This is just ordinary capacitor, ordinary batteries, ordinary resistor, but then they have two resistors that they put two arrowheads. And they call that time-varying potassium conductance. They call that time-varying sodium conductance, because this is where the potassium comes in, this is where the sodium comes in. They call that time-varying because unlike this one, where you can just say this is 5 ohms, they cannot put say what many ohms here, because they found that they need to, you have to solve the differential equation in order to calculate what is the conductance. And they found that changes with time. So that's why they call it time-varying conductances. So even though they did not know, even though Hashiaki did not know that what this, but they at least have the equation, because the equation that they produced from empirical methods, they're very, very ingenious scientists. Through careful measurement, they produced the equation, that of course very complicated, and then they put this in the computer, and sure enough, they were able to generate the action potential. No one has been able to do that before, and this paper still is a classic today. It's taught in every course in neurobiology as well. Okay, now, but there's some problem with the Hodgkin-Huxley model, because both Hodgkin and another very famous scientist called Cole, who many people thought, by the way, should have shared the Nobel Prize, with only Hodgkin has got the Nobel Prize. Many people thought Cole should as well, because of his important discovery. But both Hodgkin and Cole were shocked to find that the small signal AC impedance they had measured from the axon impedance of a squid axon had gigantic inductance. They found, they measured this in the laboratory, and they found that with an instrument, even in the 50s, with some really found that they have inductance in the order, say, like 5 henries. And then they found also that these days, DCVI curve, and DCVI behave like a rectifier. Now this is shocking, because first of all, an inductance of a few henry is a very big one. Those of you who may not know about the electroengineering, I will show you how big is 1 henry. I'm carrying a big heavy thing, about 10 kilo, and it is 1 henry. This is just 1 henry. Okay? So this is shocking, because what is measured in the lab said it should be more than 5 times like that. There is a huge magnetic field. No one, of course, has ever been able to measure that in our brain. It says that every axon must have many, many of these things, and no one can explain why. So there's a cartoon to emphasize the anomaly or the paradox. That our brain, if you measure them, the small signal will tell you that the brain should have rectifier all over, diet, and should have big inductance all over. Of course, no, this never existed in the brain. That's the unsolved problem. nobody has can explain why. You know, why is it and to show you that this is a major embarrassment for the biophysicists, because the measurement tells you something that is impossible to have. And in fact, Cole, this is the gentleman, and I say many people should have shared the Nobel Prize, but did not. In fact, USA was very upset when only Huxley got the prize. So USA, the president of the United States, awarded him the next year the USA National Medal of Honor, which is the highest honor in USA, just like next to the Nobel Prize. Anyway, so this is a very distinguished scientist, and he said in the book, he has a big book, said that the suggestion of an inductive reactance anywhere in the system was shocking to the point of being unbelievable. So we're talking about distinguished scientists like him and Pasquinati that were totally embarrassed and shocked to why that is so. Well, it turns out that the time-varying conductances in the Huskin-Huxley model that you've seen with the 2 RL are not time-varying conductances. They are in fact memristors. And I have produced the equation just from the Huskin-Huxley equation. I can produce the memristors. And for example, this is now a potassium memristor, this is a sodium memristor, and there is nothing time-varying at all. And once you replace them with a memristor, then there is no more question about inductances, because the memristor exhibit this behavior that is predicted. And so let me just quickly show you. The potassium memristor in the Huskin-Huxley model is just with the current is a conductance times voltage, just Ohm's law. Except that that conductance is not constant, depends on the state variable n, where dNdt is a nonlinearity. It's very messy, but don't worry about it. It's a function of n and the vk. So that's a memristor by my definition. And if you take this example and you simulate in computer, you will see that I'll say at 200 Hertz, it has the zero phase shift property. So I've just shown you that the potassium memristor, as I defined it, has zero phase shift property. And if you apply sinusoidal signals, you will see that it has pinch hysteresis loop. These are pinch loop. And as you increase the frequency, the loop area gets smaller and smaller, eventually becomes a straight line. This is a fingerprint of memristor. So I've just shown you that the potassium memristor, potassium ion channel are in fact memristors. It turns out that in this generalized definition, you can prove that it is possible to apply a DC battery. When I say that memristor has no DC reactor, it's the ideal case. In the generalized case, you did have a DC reactor, and the reactor looks just like that for the potassium memristor. And now for the sodium ion channel, I have shown that it is also a memristor. It's a current, sodium current, is an Ohm's law, it's a conductance times the voltage, except that the conductance is not constant. But it depends now on two-state variables called N and H. Each one is a state variable with two state equations. And from the Huskin-Huxley model, I can extract the equation. These are the equations. So I have just shown you a sodium memristor for the Huskin-Huxley model. And if I put this in the computer and apply a periodic signal, you can see it has zero phase shift. So it passed the first test. It has to have zero phase test to be a memristor. And then apply a periodic signal, sine wave, and you can see that at higher frequency, it has a pinch loop. The loop is a little bit more complicated, but it's pinch. What's important is pinch. But it also shrinks. A higher frequency, it gets smaller and smaller, eventually becomes a straight line. Perfect example of a pinch hysteresis loop. So I've just shown you that sodium memristors are also memristors. And To summarize, the correct Haskell-Huxley model should be replacing the time-varying conductances from the Haskell-Huxley model by the sodium and potassium memristor. And because they have DCVI curve, you can find, by theory, calculate the small signal circuit. This is the small signal equivalent circuit. You can see there are inductors all over. And this explains the anomaly. So the anomaly that has been solved for many years is now finally solved and explained. And you can find the DCVI curve now on my new model with the Memristor, potassium sodium memristor, and it has this total VI curve, which is like a rectifier. I have just shown you everything that has been observed without explanation, now completely clear because they are just memristors. So to summarize, I've just proved to you that the synapses are memristors. I've proved to you that the actions are made of memristors. Therefore, our brains are made of memristors. And if our brains are made of memristors, this is now for your future generation, young engineers here. Time is ready now for you to build machines. Now, they have like brain because we now have the correct ingredients. We have now the right component, the right stuff. Memristors are the right stuff for making brain-like computers. I think this is one most important message of my talk today. Memristor is not just memory. It is the essential component to build a machine that behaves like a brain. But this new result, but it's also interesting because it has other applications. I've just shown the voltage-gated channels are memristors, and that record that every memristor has a unique signature. So if you were, imagine someday, each one of us will have a database where all of our sodium memristor, potassium memristor, chlorine memristors, they're different ion channels. They will be all, because they are unique, physically are unique. So you will have that in a database, and then there is such a thing that as you get older, you develop a disease. These are called ion channel disease. So every voltage-gated ion channel is a memristor identified by a unique set of pinch hysteresis loop. Including when you have ion disease, you will have a pinch hysteresis that is different. So therefore, you can have a digital lookup table someday that can be compiled for automatic diagnosis. You can imagine that you have a healthy database of your healthy ion channels, and 50 years later, when you get older, you have a disease that is suspected to be an ion channel disease. You will have an instrument that measure your pinch hysteresis loop, and if it looks different from the database, you know that you are sick. You can identify the disease. And this will include many sickness called channelopathy is the new name for diseases that originate from ion channels. Now, these are all possible in the field. Epilepsy, myotonia, migraine, diabetes are all diseases of the ion channels. Someday, one could imagine to have a database where people are diagnosed whether you have one of these diseases or not. Okay, now the last part of my talk is about real application. So far, I've given you the definition and what is memristor, the ideal one and the generalized one. Ideal one has a single point, otherwise it smokes and burns. The general one can have DCVI curve. All of them are new concepts. But now, I think you are here mainly because you want to know what application you can have the next 4 or 5 years. And I will tell you the following. The paper has been published in 2010, in fact already, that shows that you only need 2 memristors to build all Boolean functions. You know that to build a computer, you need AND gate, OR gate, or NAND gate, NOR gate. Every one of them are using transistors, and you need many transistors. Now, this paper shows that you only need 2 to build any of the 8 16 Boolean functions. In particular, this is a circuit that it has only 10. If you count, each one of these is a memristor. Memristor, remember in this topic, it's just like a switch on and off. Each of these is memristor, 10 of them. This circuit alone will allow you to get full addition. This has been published already, both by HP and by this paper, that you only need 10 membristors to make a full adder. If you now compare to what you have in your iPad or your computers, the full adder is essential. Using the current CMOS full adder, I counted them 50 transistors. You need to have 50 transistors to make a full adder. Now, if you were a member, you need only 10 of them, so only 1/5. But not only 1/5, they are much more smaller because memristor, can shrink eventually to 1 nanometer. It's much smaller. So this is significant because all of you have known that people say that Ohm's law is coming to an end. The Ohm's law says the Moore's law says that every 2 years the computer becomes twice as powerful. But we now know we are coming to the end where this is no longer going to be true. Instead of making transistors small and which is no longer possible, however, then this what's called implication logic is this theory that allows this to happen. Permits extremely dense digital circuitry and low power operation. And when utilized in hybrid integrated circuit may enable significant increases over current computational capacity without the need to scale transistor size down. In other words, you can actually extend Moore's law now further by not making transistors smaller when it's not possible, but using memristors. Because memristor, you need not only much smaller, you need much fewer elements. Now, so you can now, in other words, make the same functionality, but using fewer elements, and of course smaller, and then consider less power. I'm going to show you 3 examples that to demonstrate what I mean. There is a device you can buy in the electronic shop called a PTC, or positive temperature coefficient thermistor. It's just like a resistor where there is a change with temperature. And there's an NTC, which is a negative temperature coefficient resistor. If you take 2 of them in series and connect a battery, you can show that you can have oscillation. This is quite amazing because all the engineering that you learn from electronic circuit said if you want to build an oscillator, you must have an inductor and capacitor at this one of it somewhere. Here you can see there's no inductor, no capacitor, a single battery, and yet it can oscillate. That's what I mean by new functionality. It's impossible to do this without memristor. You're going to need an inductor, capacitor. Now you don't need them. You just have a memristor. And a more interesting thing is, it was mentioned earlier that short circuit, this is what I designed 30 years ago. I have proved 30 years ago that the simplest electronic circuit that can generate chaos means a waveform, like an oscillation, except that in an oscillator the waveform is periodic. Chaos is not periodic, the waveform is random, that kind of thing. I have proven that the simplest possible electronic circuit to have chaos is that you need at least 2 capacitors and 1 inductor, or 2 inductors and 1 capacitor. You need 3 energy storage elements. It's impossible otherwise. And you also need the nonlinearity, the nonlinear resistor. Now, one of my former PhD students showed just a few years ago that you can produce chaos with only 1 capacitor, 1 inductor only. Remember, it had to be 3 by theory, but now with a memristor, and remember, to have chaos, you need 3 energy storage and you need a nonlinearity. Now, I only have 2, it has only 1 nonlinearity, so the nonlinearity is doing 2 things. It plays 2 roles. It produces the nonlinearity and it produces the dynamics. The reason you need 2 capacitors is a unit dynamics, energy storage. This produces the 3rd dynamics. And this is the equation. This is voltage is equal to Ohm's law and current, but the resistance is not constant. Depends on x, and x is a state variable obeying a differential equation. This is one example of a memristor, a generalized memristor. By the way, this is active memristor, which means that if you build this, you can actually build this, and this is of course complicated right now, but this can be only thing. It's made up of op-amps and transistors, and of course you need a battery because these are active. But the point is, if your memristor is active, you will have to. It's impossible to build with a device without battery. So you need battery if it's active, and so you cannot get something for nothing. Okay, you have to pay for it. You also then means you have to have energy. And what this circuit shows is that you need one active memristor, and it will produce chaos like that. Okay, it just shows you that this is not period. This is the current of the inductor. This is the voltage of the capacitor, and it's not periodic. And if you plug them in the plane, you don't have a single loop. You have something that never repeats. That's why it has some kind of a surface. This is called a strange attractor. And if you take one of these waveforms, the voltage waveform, and put it in a spectrum analyzer, you can see that it has a continuous spectrum. So unlike in this period, you will have spikes, discrete time. It's continuous. This proves that this circuit is in fact a chaotic oscillator. And so I've just shown you that a memristor can decrease the number of elements because it can serve more than one function at the same time. And the last example I will show you is take the sodium memristor. If you imagine go to the sodium memristor in the Husky and Huxley model I just showed you earlier, you take that out and you connect a resistor in series with a battery. Again, there is no capacitor, no inductor, and this is the sodium memristor. This is the equation you've seen earlier. And you can show that there is oscillation. So it's not chaotic, but it's an oscillator. It was impossible for to be built an oscillator without an inductor capacitor. Now I've shown you with a single sodium memristor, I can have oscillation. In fact, if you connect a memristor with another resistor, the whole thing is equivalent to another memristor. So therefore, I would do that. I would take this resistor and I combine them into one memristor, and so it becomes even more fantastic is that a single memristor with a battery across it will become an oscillator. It's fantastic. It is unbelievable, but it is happening. So the memristor has many applications. And if you want to have one word, a sentence to remember what it can do, is I call it more for less. It's just like when you go to the supermarket, there are always advertisements. The store advertisement say you buy one item and get one free. That's what a memristor is. Okay? You get more for less, and smaller, and less power. And that's because every memristor is endowed with three things that you don't find in any other element. It has nonlinearity, it has dynamics, and it has dissipation. And this is fantastic. You get all these three things, and if you think of evolution, think about life. Why is it that the Huxley model had to have memristor? It turned out that if you look at evolution, this nonlinearity, you can show that it is dynamics and it is dissipation. So to evolve means that you need to have components that will have this kind of function, and the memristor is the only element that has all three. So this is one reason why you can expect why you will find in living systems. And finally, let me come to the last part of my talk, which I think is perhaps the most interesting. I will not try to talk, the title is past, present, and future. I've been talking about the present, and now I want to talk to the real past. So I said the pre-HP Memristor. HP means 2008. Before that, pre-HP. And it turns out that we have just published recently an article showing that the first Marconi, the first Marconi radio was using a whisker and galena crystal. Those of you who know about a bit of the history of radio, we know that the first radio is just that simple. We just showed recently that galena crystal is a Memristor because it has a pinch hysteresis loop. So you can say at least that the Memristor is already used not only in Sir Humphrey Davy's electric lighting, but some years shortly into making radios. And since Humphrey built the first electric lighting, many electric lighting was introduced shortly after that. There were mercury bulbs, there were sodium bulbs, and many other kinds. And so I looked at a book in 1948 that have a summary of all these devices, electric lighting. And so that we're talking about in the 1920s, 1930s. And I sampled some of them. They all have pinch history. I got it pre-1948 because this book that I saw that had all these electrical lighting devices, all that this look. Of course, the author doesn't know what it is, but it doesn't have a DCBI curve, so they have all these things, and it's all pinch. So these are in the 20s. So after the Marconi radios, we have all these bulbs, and then, but let's fast forward to the 60s. This is the first paper that I've seen in 1962 where it is really solid state. Remember I told you in my 1971 paper, I have already built a Memristor, but this is impractical. It's not solid state. You need a big box of op-amps and batteries. We want to be practical. You need a single device, solid state, very small. The first such device was published already in 1962 by Hickmore. He didn't know, of course, it was a Memristor. He simply said it has memory. But they always try to publish. They never can publish a DCBI code because obviously that's what they want to do. But obviously they have burnt out the device and they were embarrassed, of course, to admit. So they do the next best thing. They put it sideways and they get pinch hysteresis loop. See, they're all pinch hysteresis loop. And interesting enough, in 1971, when I published my paper, there was a paper by Japanese, Matsuda. He published a device about in the same year, maybe 2 months later, that shows a pinch hysteresis loop working. He measured it. So already, in my paper, there is already a Memristor that exists that I just didn't know, a real Memristor. But of course, we credit the real Memristor to HP because Matsuda doesn't know it was a Memristor. But now we know it is. And shortly after that, 1972, another similar one. It's all pinch. Okay? And then very quickly, post-HP. Now after HP, 2010, for example, these are a sample. There are many papers after HP that are all pinch loops. After HP, everybody realized that these are all Memristors. So I just sampled some of them. They're all pinch loops. And so now I talk about post-HP. Post-HP means after the papers, some of them I show you are pre-HP. Now I talk about post-HP. And these are more pinch loops. Every one of them has a different year, just to show you that these are all Memristors. And this has all been published without the author knowing they are Memristors. Now, because they know, and these are all solid state. So these are the devices that the industry wants, because these are the devices that will make the future cell phone, the future iPad, the future computer. But my interest today, and I hope some of you, is that This is not, should not be your main interest because this is so simple. There's no more constant involved. It's just building the device in the mass production. There's no more theory involved, except the material. You have to look into the material property, and it is what engineers, what scientists are doing now. It's non-trivial because every one of them has a different material. So Memristor is not just titanium dioxide. It can be made of anything. But every one of them, you have to go into the material and understand why it is behaving like that. This is the difficult problem. Nobody has done that yet. And someday when they find the theory, but again, it will be different materials. It will be ridiculous to think that there will be one theory because you can have vanadium dioxide, you can have titanium dioxide, you can have tantalum dioxide. There are all kinds of, they're all Memristor. This is what engineers are doing now because this is where the money is. This is where the $150 billion industry is going to come from. But now I want to show you our interest should be beyond that. This is a recent example of organic. Now finally, all of the materials are inorganic. Now we are going to organic. This in particular, this is paper published in physical chemistry. You can see it's pinch, okay? And more recently, this is where you and I should be more excited. We talk about biological memristors. One of the papers that was fascinating was an article was published recently called "The Sweat Ducts Make Skin Memristors." In particular, this is by the way, a picture of a lady, and the back he was taking a sunbath in the beach with her son. And you can see this sweat, perspire. It turns out that our body is covered with all the sweat ducts, and the sweat ducts, people thought in the past are just resistances, but a group of scientists in Norway in 2012, Johnson, for example, and Martinson in 2000, they measured these tattoo wires on the arm, and then they measured the pinch hysteresis group, and they found that this is the sweat duct are just like a device with a hole with the liquid inside. The liquid conductivity changes because of the degree of sweatiness, and they found that when the signal voltage and current, the red is the voltage, the blue is the current. I cut off this part, goes through zero at the same time. So it has zero phase shift property. And if they plug and they look, the item is pinched. So they have published already several papers to show that the sweat duct in your skin and my skin are in fact membristors. But of course, since our body is just full of sweat ducts, it's interesting, our body are covered with membristors. Well, like that, that's what it is. And now, about the same time, a paper in the IEEE spectrum, an article shows that blood, this is a hemoglobin. If you put the blood and collect it into a little tube, you put two wires, the paper shows that it behaves like a membristors. So I've just shown you that biological system is full of membristors. And I think the reason is clear now, because memristor is nonlinear, dissipated, dynamic. You need all the things for life. And memristor has all those things. But the most exciting thing is something that happened last summer, but this time I gave a lecture in Canary Islands. And in the lecture, there was a Russian scientist happened to be in the audience, and he happened to be a botanist. So we talked about plants. And after my talk, he came to me saying he believes that something he observed he was quite a good scientist, Russian scientist, and a botanist. So he is making measurement, electrical measurement. It turned out that plants, I didn't know it until then, had actual potential, because plants have to communicate. It doesn't have neurons, it doesn't have action, but it has actual potential. And so he made measurements, and he told me that he thought he had seen measurement had pinch hysteresis group, and he asked me, are plant membristors. And I told him, very simple, go back and see if it's pinched. And he went back and he published a paper and he put my name there because I suggested what he to do, and he found we just have a paper just came out which shows that plant membristor, and I'll show you two examples. This example is called, this is a plant that somewhere this is called the Venus fried trap. What happened with this thing is that they have lips, and the lips, as soon as something touch it, say insect, you will immediately close. Very quickly, and then put the insect becomes a dinner. Okay, let's go Venus fried trap. So, Professor Volkov attached two electrodes to the back side of this thing, and he applied a sine wave. So this is the instrumentation. He measured the current and voltage by putting this the enlargement of that. And sure enough, he found what I suggested. There's the pinch hysteresis loop. So the Venus trap is a membristor. By the way, this is the picture. When it's open, it is a trap, and then when the insect touches it, this thing will close. So there's a huge axial potential has to be generated to close that. Anything like that obviously requires something that looks like the axon, and that's why this is a membristor. Now another plant is called the Mimosa pudica. This is another plant. This is what it looks like. The Mimosa pudica has the property that in the daytime it's normal like that, but when the sun comes out at night, the leaves would fall just like they want to sleep. Okay. And so it opened, and then that thing. Well, Professor Walker believed that this was a membristor. He put two electrodes, and he measured it VI curve. It's pinched. So, Mimosa pudica are membristors, and he believes that there are many others. So plants, in fact, are membristors. You may not be so interested, you're a botanist, but it's interesting. It's all about life. Anything that's living, it seems that you need membristor. Indeed, this is a picture of an amoeba. This is another professor from England, Adamaski, Professor Adamaski. He is very famous and published many papers showing the amoeba. You know, amoeba does not, it's only one cell. It has no brain, no lymph, no axon, no synapses, and yet amoeba can be very intelligent. And so he believed, Professor Adamaski believed that maybe, suspected that maybe amoeba are membristor as well. So here is the experiment. There are two electrodes, silver electrode. This is part of the amoeba. Two electrodes, and he put in a measurement, and sure enough, you got the pinch hysteresis loop. So amoeba are also membristors. And so I've shown you, I'm now coming to the end of my talk, toward end. I've shown you the past, starting with the HP paper, the post-HP, and then now we want to go back to the prehistoric. Turn out, remember anything that has ion channels, we now know that are membristors. And there was a paper published in 2007 that shows for the first time that there were jellyfish. You know jellyfish, they were able to find jellyfish in the fossil record 500 million years ago. And jellyfish has to have ion channels. So you can project 500 million years even back from Sir Humphrey Davy and say that in fact there's a nature already has a membristor 500 million years ago. And so all of them are membristor, because if there's one sentence you want to remember today about membristor for the rest of your life, is simply, if it's pinched, it's a membristor. That's the simplest thing. So as a timeline, now I summarize what I've just shown you. 1971 is where I published the paper without realizing that in 1801, 1 year after Alexandra Volta made the battery that actually led to Davy producing the world's first man-made Memristor. And now we know that it can go back 500 million years, and we already have a living Memristor, and possibly even before that. And then the pre-HP is 2008, okay? And you have seen many examples already of all the pictures that there, and you have seen post-HP, many more, and now you also show one molecular Memristor, and of course there's future. So Memristor, in other words, is everywhere, and whether you like it or not. But the important thing is that if it is everywhere, if nature has evolved in different systems, and they all have used Memristor, obviously Memristor is a powerful element that you can use for other purposes. Now I want to show you a video of another Memristor that was just based on a paper that was just published 2 months ago. And this is I will explain to you what this is, because this paper was just published in Material Science. It's by a group from the Material Science from Berkeley, Professor Wu, and he published this paper just very recently, but he was already honored by President Obama. In the United States, you may not realize that every year, the President of the United States would invite 6 young scientists out of thousands that are selected to be the most outstanding publication. Professor Wu is one of them. He was invited. He had been had dinner with Obama. He was so proud of that, and it is based on this work. So I will tell you why this is interesting. This work is just think of this. I don't have much time, but just to tell you that this green thing and the yellow thing below it is made of vanadium. Vanadium dioxide, and mainly and chromium together. And I don't have time to get into the details of this, but I have a picture of the real device. If you want to see it, it's working. And depending on the room temperature, say at room temperature right now, you will see, we're talking about nano, we are talking about micron scale. And this is about, I say about 10 micron, but you can make it much smaller. This is the operation motor. And it's made of the following. There's one coil, three coil, another 3 coil, and then 2 things have to be connected together here. Now the interesting thing is that this thing depends on temperature. As you change the temperature, this coil becomes bigger in diameter. The shape is always the same with a connection there, but it becomes bigger as the temperature increases. But of course the length is the same. The length of the wire is the same. The vanadium chromium is the same length. So if you have got a bigger diameter, you have got a fewer coil. So you can apply voltage, and the voltage is going to heat this up. So before the voltage, this say you have 3 coils, and this is the connection. At 3 volts, it becomes bigger diameter, so you have only 1 coil on this side, and it's connected to like that. So you can see the property of this device is very interesting. The voltage is going to change the diameter, and as you change this, you're going to have a torsion, a twist. So when you twist something, you have force. So this is quite interesting because Professor William asked me just 2 years ago, could this be a Memristor? And so I said, if it's pinched, it is Memristor. I said, measure the VI curve. And sure enough, he went back. 2 months later, he came back and showed that it has pinched hysteresis loops. It has pinched hysteresis loop, as I indicated there, and it also strings. As the frequency increases more and more. So the paper that was published, it's not about Memristor, mainly it's about this wonderful strength material that has this property that this is nanoscale, But because of this twisting action, it is quite amazing that when they suddenly twist to higher voltage, you can put in a little object there, and it will take it. You will throw it out like a catapult, like this a catapult. If you put in a little thing and then you release the thing, it's exactly the same mechanism. Except this is now a micro catapult. I'm going to show you a video in a few minutes, and this micro catapult is very interesting. First of all, it's a memristor. That's why we're talking about here. It's a memristor, and this is the dimension 50 micron. So it's very, very small. And this object is just sitting at a little connection there. So again, this is just like a spoon sitting there. But we must realize this is a very tiny thing. It's 50 micron. And I asked our professor, what is this object? It looks so big here. He said it's nothing but just a dust. Your sandpaper, a sandpaper, when you do something, there's a lot of dust. It's just one of those dust. You might think it's nothing, but this is the dust. And when you put in 3 volts, this thing was thrown. And so it's a micro catapult. But what's interesting is the recently published paper is this is the model of the human muscle. You can imagine someday we are going to be a robotic muscle, and it's going to be built out of this kind of structure, and it has to be very powerful. Remember the muscle thing? And Professor Wu has shown that this is a powerful force. In particular, they measured the force. They were able to show that this is 1,000 times, this catapult is 1,000 times more powerful than the human muscle. So you're going to have a bionic muscle that's going to be much more powerful, 1,000 times more powerful. You can catapult objects 50 times heavier than this. This is unbelievable. Usually, if you want to catapult something, you have to be very heavy, right? But they have made this measurement, and the object is more than 50 times than the weight of this. This is nano structure, okay? And it is faster. It's very fast. This is the paper that just appeared, as I say. And again, they put in my name, although I have no contribution. Only to tell them that if it's pinched, it's a memristor. And it is a memristor. So I would like to request the next video to show you this catapult action. A true memristor that is working with motion, with force, 1,000 times more powerful than the human muscle. So, and then I will finish with a brief conclusion. This is very short. Okay. Now you can see the micro object is there, and now that's thrown away. Again, the object is there. You can see it's living. It's thrown away. That is the work that led to Obama's invitation just a few months ago at the White House. So it clearly is a very substantial work. 15 microns. Okay, so this is the repetition so to show you. Thank you very much. And now I want to conclude to tell you that Memristor, of course, has attracted a great deal of attention. And this is the graph that Professor Dr. Williams sent me recently. Before the SP Memristor, there was 0 publication since 1971. Okay, and then all of a sudden in 2008 there were already it was published in in May. So only 6 months, there already quite a few publications. But 2009, 10, and 11, I was told that this is going exponentially and it's continuing to exponentially. So you can see that there is a great deal of opportunity, and this is the time for the young researchers here to get involved. This is because there are so much things yet to be discovered. It's like this is the time where the low-flying fruits, you can just pick up oranges by hand. You wait another 5 years, you're going to need a ladder. So now is the time to make your discovery. There have been many papers, and there are many special issues. I'll just show you two of them. 2011, there's whole special issue in applied physics, based all of Memristor and resistance devices. And some of you may already know in 2012, not 2011, the whole IEEE, proceed IEEE was on Memristor, and you can see the interesting diagram cover here is, you can see this is the jigsaw puzzle. And this piece is the artist's conception, is the machine gun that completes the circuit element. So that was the reason for that. And then there was a special issue on the IEEE spectrum. Those of you who are interested in Memristor, there's a beautiful article written by Dr. Williams. I would encourage you, all of you, to read. It's very exciting and it is very honest. Dr. Williams related the story how they invented Memristor. Turned out it took them almost 6 years, wasting 6 years of time and $1 million without understanding why it works. And finally, one of the smart people that said they saw one of my papers earlier and thought that maybe it's a Memristor, and so that was a beautiful story that you will see in this paper. And there was one special issue just published very recently on Memristor, and there will be, I'm sure, many more. So for the last few slides I want to show you as a conclusion. I know that I'm going a little bit over time, but this is the frequently asked question, so I have a prepared answer for you. Usually in the past, people will ask toward the end, why did it take so long for the Memristor to be validated? It was 1971. Why couldn't somebody else, find something before HP? Although we know that there are many, except nobody knows is Memristor. And I have two actually interesting answers that you will be interested. One is from Max Planck, that all of you know. We all know Max Planck. Max Planck used to tell his fellow scientists that new scientific ideas do not succeed by converting contemporary scientists, but rather by their opponents dying off. This is human nature. Okay? You essentially have to outlive them, to be appreciated. And so that Max Planck, was quite interesting. But there's an even more interesting statement on a similar subject by Professor Harvey. Most of you never heard of him because he was actually a biologist, but many people thought he should have received a Nobel Prize for his impressive publications. But he never got a Nobel Prize because he, unfortunately, was active during the era of what's called the McCarthy era in USA, where almost every scientist is considered to be a communist, and so he never got it. But he's a very clever person, a very original thinker, and he had a famous statement that I want to tell you. He said, just following Max Planck, he said that new theories have 4 stages of acceptance. And this is, I like Max Planck. Max Planck is more general. He said that you have to wait a long time. But he was more specific. He said new theories essentially has 4 stages. First is your colleagues going to say, this is worthless nonsense. Even your friends would say that it's nonsense. That's very typical. And then a few years later, some of you, a friend begin to say, well, maybe this may be okay. This is interesting, but perverse. Means that you got to be crazy. It's interesting, but perhaps there's something there. And then a few years later, some of your colleagues come back and say, well, actually this is true. That's true, but quite unimportant. And then the 4th stage is people will start to say, I always said so. And so this, I thought, is what happened to, in this case, of Memristor. Thank you very much.